All right, you guys, we're going to finish off our discussion of Chapter 5 here in another relatively short lecture, at least compared to that Lecture 3. With the exception of a couple follow-up, tutorials on phosphorus cycle and hydrologic cycle that Stephen requested, that I think we'll all benefit from those anyways, okay? We are going to now move into some internal planetary processes, all right? So fitting in with our discussion of kind of global processes is what's going on the inside of our planet, right? And how does that impact our ecosystems here at the surface, okay? So we'll be talking about things like volcanic activity and earthquakes and tsunamis and some other types of things, all right? So first of all, we got to understand the Earth is split up into 4 layers. Now, you guys may have learned once upon a time, the crust, the mantle, the inner core, outer core, all right? In geology terms or plate tectonics terms, we actually we label our layers a little differently than maybe what you've heard before. Not that crust and mantle are incorrect ways to put it, just in terms of plate tectonics, we use terms like lithosphere and asthenosphere. So the lithosphere is the crust of the Earth. It's also, kind of the outer mantle. Okay, so it's essentially the part of the Earth that moves as a one rigid block. All right, it's solid, and it's the crust of the part we live on, the continental plates, the oceanic plates, and what you hear of the plates in plate tectonics are actually composed of lithosphere. Okay, asthenosphere is essentially the rest of the mantle. Okay, so the mantle now, when we get down to the asthenosphere, it's really, really hot. So much hotter than we have here at the surface. It's not so hot that we end up with a pure liquid, though. And so you kind of think of it as if you heat glass up, right? Glass, as you heat it up, becomes more and more pliable, more malleable, if you will, right? So you guys have probably seen melted glass before, or it's not entirely melted. And so the asthenosphere, if you think about it, the consistency of really hot glass, maybe not melted glass, but really hot glass. And so it takes on a property that we kind of call plastic in the geology world, right? So when we say something's plastic, that means it's not a liquid, but it's not solid in the sense that it just breaks, okay? So you could think of it as almost the consistency of like taffy or something like that. It's not a liquid, it's not really a solid, it's pliable. And that is sort of like the consistency of the asthenosphere, okay? Beneath the asthenosphere, then, we have the outer core. The outer core is the liquid part of the interior, okay? Mostly composed of iron and nickel. And then the inner core, which is solid, also composed of iron and nickel. Very similar composition, at least. Now, how do we know some of these things about the interior of the Earth? Really, it comes down to seismology, the study of wave properties within the Earth. And certain types of waves travel through liquid while others don't. Certain types of waves travel faster through certain materials while others don't. And based on our ability to measure seismic waves as they travel through the interior of the Earth, we can piece together what the interior of the Earth looks like. And so that's really where it comes to it. And we kind of run experiments on, try to set up models to show that. All right. So no, we've never dug down to actually look at a solid Earth core. First of all, it's too hot. Second of all, it's too far. No one would survive down there. It's crazy. And there's lots of radioactivity. Not a very hospitable place way down there. All right. So the part we're going to mostly concern ourselves with is the study of plate tectonics, at least. All right. And that's the process by which lithospheric plates, right? So these plates that sit on top of the asthenosphere, they essentially float on top of the asthenosphere. And how they move and what happens when they move and how fast they move and how does that affect the way that you and I live in certain areas and stuff like that. All right. And then within that realm, we have what we call plate boundaries. So we have multiple lithospheric plates that kind of move as one great big rigid block. All right. Where two of those plates meet is called the plate boundary. And this is where we tend to have our most common earthquakes, right? Earthquakes can occur actually really anywhere, but they're most common along plate boundaries, as are volcanoes, which again don't always occur at plate boundaries. They're just most common there. All right, so we're going to talk a little bit about the different types of plate boundaries first. Here's a little picture of the Earth and its plates, and you may notice that the Eurasian plate and North American plate, if you kind of look at that, they're essentially one gigantic lithospheric plate. They are kind of separated by this mid-Atlantic ridge on one side, but essentially it kind of encompasses that whole northern tier of the globe. All right, you got your South American plate, your Pacific plate, and so on. All right, so when we talk about plate boundaries, it's the interaction between those plates, right, that determines what type of plate boundary we're talking about, and we're really going to focus on three major types and what we tend to see happening at them. The first type we'll look at is what we call divergent plate boundary. So when two things diverge, that means they move away from each other. So at a divergent plate boundary, we have plate interaction where there is a spreading going on. So divergent plate boundaries, we get new crust forming. Okay, whoops, sorry about that. So new crust forming at these divergent plate boundaries. Okay, so we have this upwelling of magma kind of creates this bulge, right? And the plates, as a result of that and gravity, essentially, they spread. Okay, so if you go along some of our mid-ocean ridges, these are divergent boundaries all along, kind of like the seams of a baseball, right? And it's along these seams that we see new crust forming, and likewise lots of associated volcanic activity. Okay, so deep under the ocean we have these, essentially they're mountain ranges, right? They're just low elevation because they start way, way deep underneath the ocean. But we have these mountain ranges that kind of circumvent the globe. Okay, I don't think I used either of those words right. I'm not an English teacher. Anyways, so along these plates we have what we call seafloor spreading. So we have new crust forming at the middle of those ridges, and the crust actually gets older as you move away. There's some cool lessons on like magnetic striping and stuff like that. It's beyond the scope of what we're doing here. Someday when I teach an earth science class, we'll talk about that a little bit. But anyway, so divergent boundaries, really common volcanoes, really common earthquakes. That's where we have new crust being formed and the plates are moving away from each other. Now to contrast that, a convergent boundary is where we have two plates colliding with each other, essentially. All right? Now, not all convergent boundaries are the same. This type that we're seeing in this picture here is where we have an ocean plate meeting a continental. So here's our ocean plate. Okay, and again, I could go into a lot of detail here, but when we have two plates of differing density, okay, so continental crust, by the way, is less dense than oceanic crust, and it has to do with the types of materials that make those rocks up. All right, continental crust is a little higher in silica, which makes it less dense. We're getting beyond the scope of what we need to talk about here, but when we have one plate denser than the other one, we get this process called subduction, and this is something you need to know. All right, so a subduction zone, right, is a zone where the denser plate between two colliding plates, so subduction happens at a convergent boundary, and that's where the denser plate is forced beneath the less dense plate. Now, along our subduction zones, two common features. One is we get a trench. So the Marianas Trench, the deepest part of the ocean over there near the Philippines, is because there's a subduction zone there. And we also get volcanic activity. We tend to get these chains of volcanoes that occur along these subduction zones. Now, if I go back one page here, where do we see lots of volcanoes? See these little red dotted lines? All right. We got one that goes all the way around the Pacific Ocean. All right. You guys may have heard of that referred to as the Ring of Fire. I'm going to change the color so that shows up better. How about we go back to red here, right? So we got these areas along the Pacific Ocean here, right, where we have two plates colliding. One is an oceanic plate, one is a continental plate, so we get subduction. Where there is subduction, we get ocean trenches, and we get volcanic activity. So the west coast of the United States, all right? So up here in Washington, we have Rainier and St. Helens and Baker. In Oregon, we've got Mount Hood and the Three Sisters. Down in California, we've got Mount Shasta and more volcanoes, right? So these are called Pacific Rim volcanoes sometimes, also referred to as the Ring of Fire. We see that extend. This whole Aleutian Island chain up in Alaska is a string of volcanoes. As you go down the east side of Asia, right? Japan, volcanoes. All those little Pacific islands along the rim there, volcanoes. And those are all subduction volcanoes. They also tend to be our more explosive type, by the way. Okay? So, convergent boundaries where we have one plate being denser than the other one results in subduction. Subduction results in an ocean trench and volcano chains. Okay? And the reason we get those volcanic activity there is the subducting plate gets exposed to heat. That melts rock. Whenever you have melted rock or magma coming to the surface, you've got yourself a volcano. So, what's the definition of a volcano? It's a location on the Earth's crust where magma comes to the surface. So again, a volcano is a location in the Earth's crust where magma comes to the surface, at least occasionally. Okay? Now, third type of plate boundary we're going to talk about is what we call transform boundary. And this is the type that doesn't often, not sometimes, but doesn't often result in volcanic activity. More common on these transform boundaries are earthquakes. All right? And so a transform boundary, like the diagram shows here, they're not coming toward each other, nor are we creating a new crust by having a spreading ridge. What we're having is kind of a parallel movement, but in opposite directions. All right? So you got one plate moving this way and one that way. So we're not converging, we're not diverging, we're moving parallel to each other. Now, that does create a lot of stress along that boundary, right? So they're kind of grinding up against each other. And occasionally, as that pressure builds, there's a sudden slip that results in an earthquake. And so one of the more famous transform boundaries, famous for lots of reasons, but mostly because of the common earthquakes, is in California. That whole San Andreas fault line is a transform boundary. Okay? So not too common volcanoes, but lots of earthquakes. And some of them can be quite nasty. All right? Now, I mentioned earlier that not all volcanoes and not all earthquakes happen at plate boundaries. Some volcanoes kind of pop up on the interior of continents, and those are what we call hotspots. And probably the more famous example for that would be Hawaii. All right? So a hotspot volcano is, for whatever reason, there's sort of a weak spot in the crust, and we have this ongoing upwelling of magma, right? So again, anywhere magma comes to the surface, even on occasion, is called a volcano. So hotspots would be places where this happens on the interior of a plate as opposed to a boundary. Okay? So Hawaii is one of our more famous examples, as is Yellowstone. Yellowstone's a pretty scary one. We could talk about that one maybe in class together when the time comes. But those are examples of hotspots because they are volcanic, because magma does come to the surface, but it's not associated with an actual boundary between plates. Okay? So hotspot is a location on the interior of a plate where there is ongoing uprising of magma. All right. So what exactly is an earthquake? You know, we could probably describe what happens in an earthquake, but many of you might not be able to describe what causes an earthquake. All right? And so, first of all, plates are always moving, and that builds up stress at their boundaries. All right? And so, what happens during an earthquake is we get a sudden release of accumulated energy. Right? So as two plates are pushing up against each other with a lot of force and a lot of mass behind them, it's a really slow process, but that stress builds up over time, right? So it takes a certain amount of stress built up before the two plates can actually move a significant amount of matter, all right? But eventually, and we see this happen really pretty frequently, several large earthquakes a year if you go global on your lens there, right? You kind of picture there's this sudden motion, all right? And that's a lot of energy that gets released, all right? And I know you guys probably haven't had physics, maybe some of you have, but energy, okay, travels in waves, all right? And so as that energy gets released from that sudden shift along those boundaries, as that energy gets released, it travels outward from that focus of that earthquake in the form of waves. And the shaking and the shimmying and the moving about of the Earth's crust is really those waves of energy traveling through the Earth's crust that sort of lose energy over time as they get farther and farther away from that focus or that epicenter. All right? So these earthquakes occur along what they call faults, which are little breaks in the Earth's crust or cracks. All right? And the energy gets released as a seismic wave. So the focus of an earthquake is where the earthquake actually originates. The epicenter is the surface directly above that focus. So if this is our Earth's surface and we got this fault line here, maybe the focus of that earthquake was several miles under the surface. That's the focus. Now, if I go straight above that point, right, that's the epicenter. All right? So usually, like when you watch about earthquakes on the news, they talk about that epicenter. That's because they trace the earthquake back to its point of origin at the surface. Because the waves that you and I are concerned with are surface waves, because that's what shakes us up here and knocks buildings down and kills people. All right. So that energy travels out in waves, through the interior until it reaches the epicenter, right? That area on the ground. And then from that epicenter, it travels outward, right? Kind of dissipating as it goes. All right? And depending on the type of material above it, how fast there's lots of different types of seismic waves. Earthquake stuff's really cool, by the way. I don't know if you've ever felt an earthquake. We'll talk about that in class too, but it's pretty interesting. But anyways, all kinds of crazy, cool physics that come into there. There's a whole field of geology called geophysics. They study seismic properties and stuff. We're not going to get into that. I'm going to stop myself because I get excited. But anyways, so earthquakes, sudden release of accumulated energy due to built-up stress. The focus is that actual location where the earthquake occurred, right? The epicenter is the point on the surface directly above that focus. All right? And the way we measure the intensity of earthquakes is what's called the Richter scale. It's an exponential scale, and again, I don't have much time to talk about that, but the higher it is on the Richter scale, the more energy is in that earthquake. All right, now, tsunamis, all right? So, tsunamis are interesting because it's essentially a transfer of energy, either from an underwater volcano or an underwater earthquake, right? Or associated landslide underwater. It transfers energy through water. All right? So it's essentially an earthquake in the water is kind of how you can picture that. Okay? Now, they travel crazy fast, about the speed of an airplane. All right? Now, in the ocean, in the open ocean, they kind of travel through sort of unnoticed. It might just be look like a regular swell out in the open ocean, or even smaller. All right? Now, what happens, though, so if this is our ocean, the reason for that is the bulk of that energy in that tsunami is underwater. So you can kind of picture it as this wave of energy traveling through the ocean, this way, for example, at really high speeds. Now, when that wave begins to hit the continental shelf, right, and we get shallower and shallower, the wave slows down, for one. Luckily, it doesn't hit the shore at 450 miles per hour. It would wipe everything out. What happens is it slows down, but this bulge of water kind of builds up, and builds up, and then builds up some more, right? And so what happens is you get this huge wall of water, and some of those walls of water can be 30 meters or more. Now, think about it. 30 meters is more than 90. We're talking close to 100 feet. So some of these tsunamis can be 100 feet tall. So picture a big swell of water coming at you moving at tens of miles per hour, that could be over 100 feet high at its peak. I mean, that's crazy, 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 crazy stuff. Okay, so tsunamis are super destructive. Now, they don't tend to get super far inland, so usually a couple miles maybe of destruction. But these tsunamis take out everything. Nothing survives a tsunami that hits them. There's a ton of energy in those things. Okay, one of our biggest tsunamis killed over 230,000 people in South Asia and Africa. All right, and then of course, not too long ago, you guys might remember the Japan tsunami, right? So this is the one that hit Southeast Asia, by the way. These people are goners, unfortunately. This is an insane amount of energy coming at these people. But these big earthquakes essentially transfer that energy to water. That water travels, or that energy travels through the water in the form of a deep ocean tsunami, which essentially builds up as it hits that continental shelf and just takes out the shoreline. Intense. Okay? So that concludes most of what we're going to talk about in lecture form. There's a little bit about the ocean we'll get to in class, but that's it. You guys make sure, of course, that you're doing your associated reading to follow up on things. And reminder, we'll be getting to that test in just a couple more days, so 2 more class periods before we start looking at that test. All right? So stay on top of things.